Okay, so where's Kara? Hi, Carolyn. This is more of a memory trip, really, than anything. We'll talk a little bit about chloride extraction, and so I thought I'd take you back 36 years ago to 1989. This is a picture of the job that we were working on doing impressed current cathodic protection on for MTO, Ministry of Transportation Ontario, here in 1989, and they had heard about this process that had been developed in Norway for electrochemical chloride extraction, and they wanted to do a pilot of it, and they chose to do it on this project where we were working. And this is a picture of the pilot, or a portion of the pilot. It was a portion of one pier of the structure, the rest of which was, at that time, was having impressed current cathodic protection being done. This was installed. It was operated for its period of time, and it was removed, and everything went very well. It's actually part of the, it ended up being incorporated into part of the SHARP program in the US as one of the field study sites, and kind of life continued on from there. This is a graph showing the results from that pilot project. The blue line shows the initial chloride profile, average of, I can't remember, 4 or 6 different cores that they took within the area that was being done. From the cover, like the surface of the concrete back over here, back to the depth of the reinforcing steel back here. And you can see that the chlorides back at the steel were above the threshold. And then through the treatment, the chlorides reduced. And then there's a line on there, the green one, which was some cores that they took 8 years after the treatment, because one of the questions was, would the chlorides, redistribute or come back into the concrete more than before? Didn't really move around much. So what is electrochemical chloride extraction? It's a process to treat reinforced concrete structures for the purpose of reducing corrosion. You apply a DC current to the structure, similar to impressed current cathodic protection, but it's only applied temporarily, but at a much higher level. And by doing that, you essentially migrate chlorides away from the steel and towards the surface, and a portion of them at least go outside the concrete. And that process also generates hydroxyl around the rebar, so it generates a more passive condition as a result of the chloride to hydroxyl ratio being reduced. That's essentially the process. And in graphical form, it happens like this. The system is applied on the surface, but exterior to the concrete. It's connected to a DC power supply. When you turn it on, you charge the rebar negatively. You charge the system on the surface positively. You keep everything wet so that the chlorides can go into solution within the pores of the concrete. And then they tend to move in the direction of the current flow lines, and they progressively move away from the rebar and towards the surface. Not all the chlorides are removed, and that's probably one of the problems with this process is the name. Yes, chlorides are reduced, but it's really more of a corrosion mitigation process than it is a chloride extraction process, so that's a little bit misleading, and you definitely develop a higher pH zone around the rebar as a result of that. So after that first trial, and you saw some of the initial results there, MTO did a second trial. I looked diligently for a photo, and I could not find it. I know I have physical hard photos, but a year, I think it was actually 2 years, I think it was 1991, we did a second trial for MTO on some circular bridge columns. It was on 401, just east of the airport. I think it's Winston Churchill Drive, if I remember right. And the columns were kind of similar. This is actually a picture from Saskatchewan of a job that was done in 1994, but had a different rebar configuration. We did the work, took some cores, and the results that they got from the chloride in terms of the amount of chlorides that were reduced and whatever was significantly less than what had happened on the Burlington pilot, and it raised a number of questions. And that actually led into some research that Carolyn ended up doing a couple of years later, because I'm not sure when your research started, but it would have been in the mid 90s. And it really came from kind of, you could say, a discrepancy between these two different pilot projects. One seemed to work exceptionally well, and the other one worked, but not to the same degree as the first one. And so what kind of things did Carolyn look at in the research? She looked at, and I'd say her students looked at a number of these issues. Basically the effectiveness of the treatment with admixed chlorides versus surface applied chlorides. The effectiveness with different steel configurations, that was the main issue between the first pilot study and the second one. You've got hoop reinforcement that's very, very close together compared to a grid of reinforcing in the rectangular piers. Changes that might happen at the concrete interface as related to the concrete chemistry and the bond. Changes to corrosion rates and potentials after treatment. Data with different electrolytes, and I say that because what was being used in laboratory studies back at that time, and the SHARP program was the same thing. They were using an electrolyte that was really different than anything that was being used in the field for these actual field projects. So there was some interesting differences in the results as a result of the electrolyte. And all of this research provided laboratory test data that has been incorporated into various different, started out as being guides, but now in the standards and the codes. Like if you go to AMP and you can download the standard for doing chloride extraction, some of these parameters that were studied are incorporated into those code documents. So how did this whole job actually perform over time? And I'm going back now to the original one in 1989. And so this is the Burlington Skyway. And for perspective, for the people here that are not from Toronto, which is probably most of you, Burlington is about 40 miles, 30 miles east of here. And Burlington Skyway is kind of west. We're east of Burlington, that's correct. And so if you go out the front here down to Gardner Expressway and you go west and you go out there, depending how traffic is, between a half an hour and an hour, you're going to end up at this bridge. And so, that project, which is really remarkable in the sense that it's the first kind of full-scale project of this, even though it was only a small section of the structure, it's the first kind of full-scale application in North America. And MTO took a lot of interest in this, and they monitored it, I would say, intensively over a long period of time. In the first 8 years, they went out every year and took cores and a whole bunch of other things. And then after the first 8 years, they went out at 15 years and did a detailed survey, and at 20 years did a detailed survey, and then in 30 years, there was only a visual survey done, but basically none of the people that were involved in the project from MTO were still working there at that time. So I would say in recent years, the level of enthusiasm about it has declined just because the new people don't know. But so on that original pilot, the left column here, the north face, one of the faces of the pier was left as a control and was not treated. And the three other faces of that pier were treated. And so basically you can take a look at the corrosion potential data, and you can see that the corrosion potentials, which were all in the uncertain or active range prior to treatment, shifted to be in the passive range after treatment and have remained that way at least over the 20 years that it was monitored, that corrosion potentials were taken out there. And the untreated section, although it did improve initially afterwards, and if you want to talk to me about why, we did eventually figure out why, but it was a temporary benefit, and it did revert back to kind of the conditions it was before. MTO also did corrosion rate measurements out there using linear polarization. The results parallel the corrosion potential data. On the untreated face, the corrosion rates really didn't change very much. I mean, there's seasonal changes because of weather conditions, wet, dry, hot, and cold, when they go back at, even though they went more or less at the same time of year. But the treated faces of the pier, the corrosion rates dropped in a very significant way. And probably the most interesting part of the data, because it contradicted certain things that were seen in the research that was done in the lab, including the stuff at University of Waterloo, as well as in the SHARP program, was that some of that lab research had shown that permeability of the concrete increased as a result of chloride extraction, and also that the electrical resistivity of the concrete also in some cases increased as well. Yet the results from the field, actual field sites, were exactly the opposite. And this is one of those things where you really have to look at the details of what was done in the different cases to figure it out. And this whole issue comes down to the electrolyte that was being used to do the work. So in the laboratory work that was being done, and the SHARP program, and I think you just used the same as what was being done there, they were using sodium-based electrolyte. Sodium borate was the common one that was used at that time. And in the field, we were never doing that. We were using basically lime water, so calcium hydroxide solution. And so this effect, and it also plays in with some of the bond issues and whatever. So, you know, when you draw all the sodium towards the steel, you know, and you create those salts are very soluble, unlike calcium salts. So what you see happening when you use lime for example, is that it plugs up the pores of the concrete, particularly at the surface, and it makes the surface permeability go down, you know, a lot. And you see the same thing happen for electrical resistance reasons as well. Just to kind of close with a few different examples and other things. So they did the detailed things for 8 years. Then at 15 and 20, they did detailed inspections as well, but not on an annual basis. And then at 30 years, they did a visual inspection. And you've seen some of the data already. I thought I'd close by just showing you a couple of other projects and how these same things are being related and in the same data. So one of the early jobs, it was actually the second job that was done in the United States, was in Arlington, Virginia, on a bridge deck. It was done in 1995. Pictures of installation here. And in 2021, so more 25 years later, a company called Nexco West, which does a lot of monitoring, a Japanese company, does a lot of monitoring and particularly uses infrared thermography. They did study on a number of bridges for VDOT, Virginia DOT. And this, so that's their raw data. This is the delaminations that were identified by the infrared thermography on the 5 different spans of the deck of the bridge. And then they did a hammer sounding, VDOT did a hammer sounding survey to verify the infrared results, and they're basically the same. And the 2 spans that were treated as part of that project back there are the 2 on the right, spans 4 and 5. And so you can see, in terms of actual concrete damage, the difference between the treated and untreated ones. And finally, another project that was done around the same time, a couple of years later. This is a bridge in Winnipeg. It's actually not far from where I live. And this bridge was built basically in 1959. They did rehab to it in 1998. And at the time they did the rehab, they did chloride extraction on one of the piers. A few years later, we did impressed current cathodic protection installation on another pier, and one pier was maintained as a control. And you can see the effect again in terms of the reduction in the amount of cumulative concrete damage. So from the repairs that were done in 1998 until 2013, when they did the next round of repairs, you know, there's a big difference here between the amount of additional repairs that were required on the pier that had chloride extraction compared to the control pier, which just had concrete repairs and no other things done. So with that, chloride extraction is a corrosion mitigation strategy. It can provide long-term corrosion benefits. It's not applicable in all situations. I think that's one of the things you learn from the research and also from the field. And without question, the work that Carolyn did and a number of others has helped to define the parameters that are used today for the application of that process. So thank you very much, Carolyn.